2022, question number 6, the second vaccine-related question on this paper, if you can spot a theme. So we want to write the chemical equations for process 1 and 2. So process 1 is the hydrolysis of ethyl orthosilicate to orthosilicic acid, and process 2 is the decomposition of the acid into silica. Okay, fine. So process 1 is going to be SiO CH2 CH3 4. So it's basically SiO like that. Okay, and it's the hydrolysis. So we're going to react it with water, and we're going to make SiOH4. So we're going to, I don't know exactly how this will work, but we're essentially just going to break this, or you could break this one, and then we're going to bond it to an OH instead. Okay, so it should be fairly clear that I'm going to be making the alcohol here, ethanol. So I'm going to get ethanol is CH3CH2OH, so I'm going to write it as C2H6O just to make it easier to balance. Obviously there's 4, so that's going to be a 4, and then I just need to well, if I'm going to break each one of these, so I'm going to need 4 waters in order to do that. And then you can double check and make sure it all balances, which it will, because I've got the so when I take this off, I need to put an extra hydrogen on, which gives me one of the hydrogens here, and then I replace it with the OH, which gives me the rest of the water. Okay, fine. Then I have the decomposition of the acid into silica, so that is going to be SiOH4, and it's decomposition, so it just goes into SiO2, and obviously plus something else that has got hydrogen in it, and oxygen as well. And you can see I'm going to have 4 hydrogens and 2 oxygens, which is H2O, and there's going to be 2 of them. Okay, nice and straightforward. Then we have an enthalpy calculation, so calculate the standard enthalpy change of this reaction given the following data. Okay, now, depending on how confident you are, for this one I would look and I would say, okay, well, look, I've got silicon dioxide here and I've got silicon dioxide here, so I'm going to need that one as it is. All right, and then I've got NaF here in the products, but I've got 6 NaF here in the reactants, so I'm going to multiply that by -6, and then I've got HCl here and I've got 6 HCl here, so I'm going to times that one by 6. Okay, and then you can just do it, right? So I can just do that calculation and I'll get the answer. So I do minus 56.7 times 6 minus 100.3, and then because I'm multiplying it by minus, this becomes a plus. So I'm going to plus 61.5 times 6 gives me minus 71.5. Okay, now if you want, you can write it all out again, or we can just put it in here. We can put the coefficient at 6, 6, 6, 6. That one stays the same, and then this one I'm going to turn it around and times it by 6. So it's going to be 6 H2O plus 6 NaF becomes 6 NaOH plus 6 HF. And then you can cancel it all out, and you'll see. So 6 waters cancels with 6 waters, 6 sodium hydroxides cancels with 6 sodium hydroxides, 6 HFs cancels with 6 HFs, and that should leave me with SiO2, 6NaF, 6HCl, 6HCl, 1H2SiF6, 6NaCl, and the 2H2O. Right, just in case you want to double check it. Process number 2 is thermodynamically favoured but slow, which is why it requires a catalyst. So process number 2, remember, is this decomposition step here. The equilibrium constant for the reaction is K equilibrium equals 1 over SiOH4. Does that make sense? Yes, it does, because this is going to be a solid, and water we are not going to concern ourselves with. So the equilibrium constant is going to be 1 divided by the concentration of the acid, where SiOH4 is the equilibrium. Oh, and then we've got this expression here for the log of the concentration. And I've got a term divided by T and another term. And then I'm asked to calculate the molar enthalpy change, delta H standard, and the molar entropy change, delta S standard, for process 2. So, you know, nowhere in here, this is unrelated, right? So nowhere in here for process number 2 have I been told anything about enthalpy values or entropy values. Okay, so I'm obviously going to have to do a little bit of work, and they're giving me a nice big space here, which is great. So I know 2 things that are going to be probably going to be useful here. The first is delta G equals delta H minus T delta S. Now I like that because if I divide this equation by T, I'm going to get delta H over T and delta S. Okay, which is going to look like this thing here. All right, and the other equation that might be useful, because obviously I've got an equilibrium constant. I'm given an equilibrium constant here, so how can I relate this to an equilibrium constant? Well, I know that delta G is also minus RT log K. All right, so somehow from these 2 facts, we're going to end up with a value of delta H and delta S, because I don't know what delta G is, right? So I need to remove the delta G somehow. So I can write out minus RT log K equals delta H minus T delta S. And then I can divide by T, minus R log K equals delta H over T minus delta S. So that's good. That's starting to look like this equation a little bit. All right, and even better is I've got this log, and then I've got my equilibrium constant here. Okay. So before I do the log, it's probably just easier if I just tidy up this minus R here. So let's divide by minus R and hope that works. So log K equals, this is going to be good as well actually, because this is going to give me a negative. That's irrelevant, I think, actually. Let's not worry about it. I'm going to get delta H minus delta H over RT plus delta S over R. All right, so that's my equation. Then I can do my log of K. So log of K equals log of 1 over the concentration of SiOH4, which is log of 1 minus log of the concentration of SiOH4. Log of 1 is 0, so this just comes out as minus log SiOH4. Okay, so let's put that in. So I'm going to get minus log SiOH4 equals minus delta H over RT plus delta S over R. And is this? Let me just have a think about this now. I'm going to get rid of this minus sign. I'm going to do that first. So I'm going to put log SiOH4 equals delta H over RT minus delta S over R. And I also know from the question log SiOH4 equals minus 1680 over RT over T minus 0.605, which then, as long as I don't run out of space, means I can just write out delta H over R equals minus 1680, and likewise, it's getting a little bit tight for space here, delta S over R equals 0.605. Okay, so you've got to just be careful. This is a positive and this is a negative, this is a negative and this is a negative. Alright, so that means that delta H and delta S are both calculated just by multiplying these numbers by R. And just to be really careful, this number is just a number. R is going to be in no, hold on a second. This number here must be, because it's delta H divided by RT, whatever this number is, it must be Kelvin. And then we're going to divide it by joules per Kelvin per mole. The point is that this number here is going to come out in joules. That's like that's the last bit that you got to double check, is that you understand that because we're multiplying by R and R is given in the units of joules, if I use 8.31, that this number comes out in joules. Okay, so that 13,960 joules, I'm just going to write as minus 14 kilojoules per mole. And delta S 0.605 times 8.31 gives me 5.03, and then that's going to be just the normal units of entropy in joules, so joules per Kelvin per mole. Now, if you've looked at the mark scheme, I think there's a mistake in the mark scheme here. It's just a typographical one, because actually, no, you can see, yeah. So they've written delta H equals minus that times that, and then they've given that. That should be a minus there, obviously. Okay, so that's quite a nice question. If you compare that to the question on equilibrium, I think it was question number 4 for this year's paper, where you had to sort of, it was a similar thing. We had to derive formulas and then like work through the maths, which was way too difficult. I feel like this derivation is quite straightforward. You know, we all know this, we all know this, and I think it's not a big ask to be able to do this bit of algebra here. So quite a nice question. All right, so moving on. We then, you turn the page and you see this equation here and you think, oh my lord. I worry that actually a lot of students will see this and they'll just think, I'm not even going to bother. All right, and it's really important that if you've got time. I think in the examiner's report they did say that they felt that a lot of students have run out of time by this point. But it is, just because it looks difficult doesn't mean it is difficult, right? That's kind of what they're trying to do, is they're trying to make it look difficult, but actually it's quite straightforward. So calculate the constant A, given that at t equals 0, the autocorrelation function C0 is 1.56744. Okay, so what we can do is, this is a function C of the variables, well, if I know the radius R1 and the radius R2, and I know this constant, and it's a function, this function C is a function of time t. So in order to find C0, that is just going to be when t equals 0. Okay, and now if you look through, so you know, I can write here, instead of C, I'm going to find it a little bit more easy if I write C as a function of t. I can see that I've got t here, t here, t here, t here, and I set all those to 0. That becomes 0, that becomes 0, that becomes 0, that becomes 0. So C of 0 is 1 plus A times 1. Is that right? 1 plus A. Yeah. So then I can just, and I've been given the value of C0. So A is just this number minus 1. So I don't need to do any maths. I can just write it down. It is 0.56744. Okay. As you can see, significantly easier than it looks initially. Okay. Then we have calculate the constant A, calculate the values of the slope A and intercept B, given that C is, so they rearrange this equation into a different form, where they're giving you a form of F, so F equals AT minus B, which, and F also equals C minus C0 over this uppercase gamma T. I mean, it's just like a lot of this maths is, it's fine. Like the issue I think here would be to think to yourself, oh, I wonder what's going on. Let me try and work out what all these different equations mean and how they work. And really, that would be lovely. It would be great if we could sit down and say, okay, well, how does this happen? You know, can we rearrange this into this and make sure it's all correct? In the test, you haven't got time to do that. So really, in the test, it's sort of like you just got to crunch the numbers and not worry too much about whether or not you really understand what's going on. I'm not saying, you know, so just to reiterate, it's important to know what's going on, but under the time constraints, we have to make certain sacrifices. And the most important thing is that we can compute the answer rather than have like a perfect understanding of what the calculation is actually doing. So calculate A and B. All right, A and B. Now, at this point, it's sort of like I've got A's and B's everywhere, and I've got to decide what to do. The important thing to realize is that you've been given a value of C and a time, and another value of C at a different time. So I can't use either of these equations because these equations express A and B in terms of the radius of the spherical particles. Okay, so for the moment, I'm just going to ignore these ones. Okay, and I'm going to go for this situation up here. Okay, and let me think. So if I can work out, I know a value of t, so I know I've got t equals 1 and I've got t equals 2. So if I can work out a value of f of 1 and a value of f of 2, and I know that f equals at minus b, then I'm going to be able to set up two simultaneous equations. All right. So can I work out f of 1? Well, I know that it's c minus z0 over gamma t. I know the value of c at 1. I know c0 because I've been given it up here. I know gamma because that's also given in the question up here. And I know t because t is 1. So that looks like our best bet. So I'm going to go 1.54289 minus 1.56744 divided by gamma, which is 0.170713, multiplied by my time t as 1. Now the time t is given in microseconds, which is fine because my gamma is in nanometers per microsecond. So this is all going to work out no problem. And then this one is going to be 1.519 minus 1.56744, all divided by 0.170713 times by 2. So I work those out. I give myself a little bit more space than that because this is not going to be the end of the question. 1.54289 take 1.56744. I'm missing a 4. Just because it says to do it to the correct number of decimal places in this question. Divide by 0.170713. Okay. So I'm going to give myself 6 significant figures. minus 0.14380. 9. And then this one is 1.51937 minus 1.56744 divided by 0.1713 times 2. Got to make sure you don't type any of this in wrong. Minus 0.140792. Okay, and then I can set up my simultaneous equations. So I can have, this is going to be minus 0.143809 equals A minus B, and minus 0.140792 equals 2A minus B. I've put t equals 1, this is t equals 1, and this is t equals 2. Okay, and then you can just use whichever preferred method you have to solve it. What should I do? Let's do, this is equation number 1, this is equation number 2. I'm going to do equation number 2 minus equation number 1. And that's going to cancel my b's, and it's going to give me 2a minus a is a. So I'm going to do minus 0.140792, and I'm subtracting a negative, so it's going to be plus 0.143809, gives me 3.017 times 10 to the minus 3 equals a. And then I just need to find b. Well, I can write from here, I can write that b equals a plus 0.143809. So my value of b is just that, plus 0.143809. So b is 0.146826. Okay. Also, I feel, relatively harmless. Again, I mean, like is always the case in the Olympiad, there's always at least one question which isn't really chemistry, it's just a lot of maths, which is why they do say, I think the statistics show that if you're good at maths, if you've scored to a particular level in maths, you will generally do reasonably well on the paper. So, make of that what you will. And then it says, hence calculate the radii R1 and R2. Consider first, so now we want to know R1 and R2. So now we're going to be using, because now I know A, I know B, so I'm going to solve these. I know A, I know B, so now I'm going to solve these and work out what the radii of the spherical particles are. Now it tells me consider first solving x1 and x2 for these substitutions. Now I'm going to go straight ahead and do that. I'm not, sometimes I might think to myself, maybe I'll do that, maybe I won't. Maybe I'll try and use my own method. On this occasion, I am going to take their advice and I'm going to go for it because it's the very last question. And why would they do that on the last question? Why would they, they're trying to be nice, right? So, what can I do? Well, I know. So first of all, I'm going to rewrite these equations using my substitution. So I'm going to write A equals gamma. I really don't like writing that gamma. There must be a better way of writing it. Gamma over 2, and that is x1 squared plus a x2 squared. All right, you got to keep an eye on these subscripts, and obviously if x1 equals r1 to the minus 1, then r1 to the minus 2 is just r1 to the minus 1 squared. Yeah, power, like laws of indices, right? Equals x1 squared. Gives me that equation, and then my b equation is going to be b equals x1 plus a x2. Okay, now I've got two equations again, so it's just a case of solving these because I know what gamma is, I know what a is, I know what the big A is, I know what b is. So I've got two unknowns, two equations, so it's just more algebra. Now before I put the numbers in, I'm going to do all the algebra, just because I think it's going to be easier for me to do that. So I need to substitute one of these into the other equation. This has got squares in it, so I'm not going to touch this one. I'm going to substitute this equation into here. So I'm going to rewrite, I think it's easier for me if I do x1 equals b minus ax2, because then I'll avoid having any fractions. And I'm going to put my x1 into here. So a is going to be gamma over 2, and then it's x1 squared. Well, x1 squared is going to be b squared minus this times this times by 2, right? It's the cross term, okay? So it's going to be 2a b x 2. If you're not sure, you know, and you want to write it out as brackets, fine, but that's what you'll get. Plus, and then this term squared, because it's minus, right? So you're going to square it. A squared x2 plus my other term up here, plus a x2 squared. Okay, so now I've got an equation just in terms of x2. Okay, do I want to rearrange it a little bit? Yes, I do want to rearrange it. I think you could put the numbers in now, but I'm not going to do that. I'm going to tidy it up a little bit. How should I do this? I don't want to multiply. See, here the temptation now is to multiply this all out, but I don't need to do that. I can just bring this over here, so I can get 2a over gamma equals, and then I want my x2 squared term, so a x2 squared, and then I want my linear term, so it's going to be plus a squared minus 2ab x2 plus b squared. Okay, and then obviously we're going to be solving a quadratic, so I want this equal to 0, so these are all constants, so it's just going to be a x2 squared plus a squared minus 2ab x2 plus b squared minus 2a over gamma equals 0. I think I've made a mistake somewhere. If you've spotted it, well done. Because it is not like what I had before. So I had substitute this in. So it's x1 squared. Is that squared? So I get b squared minus 2ab x2. Okay, here we go. A squared. That's a squared. All right, fine. I remember the coefficient of the x squared being two things. All right, which means then that it shouldn't be the a squared there. Very messy. And it should be the a squared here. So that should be a squared plus a times that. Okay, all right. I'll write it all out again. Okay, so it's going to be a squared plus a x2 squared minus 2ab x2 plus b squared minus 2a. You know, to be honest, it might be worth, depending on how comfortable you are manipulating numbers and how comfortable you are manipulating variables, it might have been worth it just to like start putting numbers in earlier on. But there we go. And then, so now I'm going to put my numbers in. All right. So a squared plus a. So I should have a number for a somewhere, hopefully. Calculate the constant a. Yeah. So a was this number here. So it's going to be that squared plus itself. So it's going to be 0.56744 squared plus 0.56744. There's just no, that this is it now. It's in calculator mode, right? So it's going to be 0.889428 x2 squared minus 0.56744 times by 2 times by b 0.146826 gives me 0.1666. 3. Sorry, you can't see that. Plus b squared, 0.146826 squared. Take 2 times a, 3.017 times 10 to the minus 3, divided by gamma. Gamma. Where's gamma gone? Gamma. 0.170713 gives me that. So minus 0.013787. Oh, 999, fine, whatever. Okay. Okay, then I do my quadratic, so it's going to be minus b, so it's 0.16663 plus minus square root b squared, take 4ac, well that's a negative, so it's b squared plus that times that. Okay, so let's just do it. Let's do 0.16663 squared plus 4 times 0.889428 times 0.013787999 gives me the square root of 0.07681. Actually, let's just do the square root of that. Gives me I made another mistake somewhere. Sorry, I've lost my point. I've lost where I paused it for a second then because I thought I'd made a mistake, but I don't think I have made a mistake. So I got up to here, right, and I was gonna leave it on my calculator, and then I got a little bit confused about what was in my calculator, which is why it's nice to have it written out. So actually, let's just carry on. Let's just do 2 times 0.889428. Okay, so that is going to be my value of x2. So let me work that out. So square root 0.076819. And then it's going to be this plus this or this minus this. Well, at this point it's quite nice, right? Because I can see clearly that if I do this minus this number, I'm going to get a negative number. And seeing as my equation is, my substitution is x1 equals 1 over r1, I definitely don't want to have a negative value of x, because that's going to be a negative value of the radius, so I can just ignore my subtraction one here. Okay, so I'm going to go plus 0.16663 divide by 2 times 0.889428 gives me 0.24948, and then I can work out, well, if x1 is 1 over r1, then r1 is 1 over x1. So r1 is 1 divided by that, which gives me 4.01. What are the units? Well, I did mention it earlier on, but the whole time we've been working in nanometers, which is nice because that's probably the kind of size you'd expect for a nanoparticle. So nanometers. And then all I have left to do is then just calculate the value for R2. And so let me do that here. So x2 is going to be b take x1 over a. So I know that b is 0.146826, take 0.24948, divide negative, what? B take x1. Oh, I calculated x2. Okay, so I don't want to do this. I want to do x1 equals b minus ax2. So always useful to just have an idea of what it is that you're calculating, so that if you end up with a negative number, you know it's going to be wrong. All right, so let's try again. Let's do b 0.146826 take a 0.56744 multiplied by the value of x2 that I just found, 0.24948. Fingers crossed it comes out positive, which it does. It's that, and that's my value of x1, but I want the reciprocal to give me the radius, so r1 is 190. Sorry, look at this, you've got to be super careful here. I'm making mistakes all over the place. That's x2, so this is r2, and r1 is 190 nanometers. There you go. So, you know, it's a lot of work at the end, but it's, if you like the maths, it could be useful.